So what happened last time, I felt that I need to add a few slides to this slide set to make it more understandable. And also I put all the updates from the new steel manual, the 15th edition. So I added all the tables from there and all the charts instead of talking about two different, I'm gonna say manual versions. So in the first slide here, there is no change. This shows here some loading, and it shows a number of connectors needed, mechanical connectors or Nelson studs needed on each side from the point of maximum moment all the way to the point of zero shear. And it shows here that this N1, which is number of studs from the maximum point of moment to the zero moment, which also is going to be the maximum shear, is going to be also the V prime, and V prime is going to be the compression force that we'd like to transfer between the concrete and the steel beam, divided by the number, which is this number here, Q sub n. This gives you the capacity of each Nelson stud that you put in there. So if you have the total force that you want to transfer from this point to that point as shear, you can just take this force here divided by how much each Nelson stud is going to be taken as in shear, and with that you have total number of studs in each side. So to make it also more clear, this is a picture I was telling you about in mechanics of materials. And this shows here, if you have, let's say, two beams on the top of each other, and then you start to load them, what's going to happen? They're going to start to deflect. Since there is no connection between the two beams, you're going to see that you have here the shear flow is going to be pushing the top beam to deflect in this fashion. And with that, you are going to have this S maximum, which is going to be the shift. This means that you have some shear flow here. This shear flow is going to be pushing this section of the beam, the top beam, is going to be pushing it outwards, while the bottom beam is going to be pushed inwards. And this is what we call here the shear flow. Shear flow is going to be equal to the total shear divided by the distance, which is L over 2. So again, shear flow units is going to be kip per foot or pound per foot if you like. So now you'd like to have this connection between the concrete slab and between the beam, in our case. In order for you to do this, you need to provide connectors. And these connectors, they're going to be taking all of this shear flow to transfer it from one side to another side. If you like to design this to be fully composite, you take the compression force in the concrete, is going to be the maximum of the force that you can transfer between the steel to the concrete. So this compression force, when you do the analysis, you're going to have here two values. One value is going to be AS times Fy, and the other value is going to be the compression in the concrete, which is 0.85 F prime C times the width B times the slab thickness at the beginning. Most likely, the compression in the concrete is going to be greater than the tension in the steel. And there is no need here to have a connection to transfer the force from tension to compression to be more than what the steel is going to be able to take. And with that, you're going to have the fully composite action transfer, which means this amount of shear from this point to that point is going to be equal to the tension in the steel. So you'd like here to transfer the tension in the steel into the concrete. And with that, you're going to get the full composite action. So here's the tension at the bottom. This is going to be the compression that you allow. You don't need to take the entire compression force as a capacity of the concrete slab. Instead, you're going to be taking it equal to this tension force. As we said, this compression is going to be equal to the minimum of maximum tension that you can allow into the steel or the maximum compression that you can allow in the concrete. And as I said also, most likely the tension in the steel is going to be controlling because this value is going to be much less than the concrete compression strength. So in this case, C is going to be equal to T. And the shear flow here, which means the shear flow is going to be equal to what? It's going to be equal to V, which is the total shear, multiplied by the first moment of area, divided by I transform. This I transform means that you're going to be considering here determining moment of inertia, considering that the entire section is going to be made out of steel. We went through this exercise before in the inertic analysis for composite beams. And what we have done, we have taken the concrete section and we took the width of it divided by N, which is a modular ratio. Now we'd like to connect both of these two to each other. So the only way to connect them again is to put this Nelson studs. So next slide, you're gonna see here the Nelson studs, and you see that this is gonna be the compression, and you're gonna have compression here on the stud itself. This is the reason that we need to confine this or contain it in some concrete. Otherwise, performance of this stud is gonna be really poor. And at the end, transfer of the shear or this compression force from the concrete to the steel or from the steel to the concrete is going to be going through the shear of each one of these studs. If you take here the total force, which is T, divided by a number of studs that you provide in one half of the beam, this is in case of that you have uniform load only, like as a vertical load. You take this tension force divided by number of Nelson studs in one half of the beam is going to get you the force that each Nelson stud will need to resist. And actually, this can be the mechanism. This is how you transfer the force from the concrete to the steel. We went through this exercise and this equation before. We said that this equation actually is composed of two equations. The first equation is going to be based on the concrete strength. It says here 0.5 cross-section area of the stud of each Nelson stud multiplied by square root of F prime C times EC. And you got to be careful because usually when we work with ACI code or concrete, we usually say that this is here in PSI. But when you come to AISC, it's going to be in KSI. You need to be careful about this. This here, KSI and KSI. Which means this is going to be, most likely is going to be 3 or 4, and this value is going to be maybe 3600, maybe 3700, something in this range, KSI. The other factor here is going to be about the steel itself. I'm not talking here about the steel as for the steel beam. I'm talking about the steel for the stud itself. So this section is going to be about the concrete. This equation is going to be about the concrete strength. And this equation is going to be about the stud itself. So cross-section area of the stud multiplied by F sub U multiplied by two factors. And these two factors, one of them is going to be accounting for the group, and the other one accounts for the position. So R sub G is going to be the group effect, and R sub P is going to be the position effect. We went also through this schedule, and we said if there is no deck at all, which means there is no metal deck, I'm going to have R sub G and R sub P is going to be 1 and 0.75. In most cases, I'm going to have these two values here. Because most likely WR divided by HR, and just to clarify what is WR, what's HR you have in here in this sketch, here's WR and here's HR, which is this one, the deck height, is going to be more than 1.5, which means most likely I'm going to be going with this 2 if I have the deck oriented parallel, which means this is going to be for girders, so this is going to be the case for girders, this is going to be the case if there's no metal deck. In most cases, when you have beams, you'd like to have only one stud per row instead of having two. And in this case, I'm going to be going with this option here. So it's going to be one stud. This is going to be for beams, as we said before. It's going to be for girders. This if there is no metal deck. And when you look here at this node B, it says this value may be increased to 0.75 when E mid height is more than 2 inches. So what is E mid height? I'm going to go here and look at E mid height. What's E mid height? It's going to be maybe the average height of the stud. Usually this is going to be 2 inches or 3 inches. It's going to be either 2 or 3 in most cases, which means most likely this option here is going to be valid for us. We're going to end up with 1 and 0.75 in most cases. All right. Now I updated this table. I put it from the AISC 15th edition. So we had to take some pictures and look at the values here. This value used to be 11.6 for the half inch with no deck. Now it is 9.57. And also they added more values. If you look here, the old one used to end, the old code used to end with 3/4 inch. Now they go to 7/8 and 1 inch. So most likely I'm going to be going here with 3/4 inch. So if you're doing your homework or doing the project, you can go with 3/4 inch. And if you really feel that this number 7/8 inch, which is a 29.3 kips, let's say if you have 4,000 KSI for the concrete, or 3,000, if you feel that shifting it up or changing it using 7/8 inch instead of 3/4 inch to make the spacing of the Nelson stud about 12 inches, go ahead and do it. So let's say that I have a beam and I find out that in most of the beams on this floor system, if I'm gonna go here with 3/4 inch in most of the beams, you can end up with spacing of 12 inches. And then all of a sudden here, I have a couple of beams that I will need to have the spacing, let's say about 6 inches, because I need more studs. Now I have two options. One option is just use 3/4 inch throughout the project. And for these two beams, I'm gonna be adding a little bit more studs. This is gonna be one option. Other option is to change the size of all the studs from 3/4 to 7/8 inch for all beams to make the maximum spacing here to be 12 inches and not to go to 6 inches spacing. In a case like this, definitely I'm gonna go with the first option, which means keep the anchor diameter or the stud diameter to be 3/4 inch, and in a few beams, I'm gonna be adding here a little bit more studs. This is gonna be the option that I would tend to.
Hi, Professor.
Yes.
So in like industrial, like which one is more practical?
3/4 and 7/8.
Okay.
This is a tool that you usually work with. Okay. This is the same table, actually. This is the same table I just took here, the top piece with no deck, and just lodge it here, just in case if you don't have an access to this copy of the steel manual, so you can take it from here. And the next also slide is going to be the one that shows girder. This is going to be deck parallel. So this is going to be for girder. This one here is going to be for beams when R sub P is equal to 0.6. And this is going to be the case when R sub P is equal to 0.75. So you know R sub P is going to be for the position, and we talked about this. All right, so we went through this example already. We solved the example. We have W 18 by 35. We have concrete strength 4 KSI. Slab thickness was 4.5 inch. We have the span, and we find out that the compression, which is based on the steel, this is taken here from the previous example, was 515 kips. 515 kips. Now I need to figure out the stud and the stud spacing. Here is cross-section area of the stud. Went through this exercise before. We said that based on these two equations, one of them is going to give me 11.6, which is based on the concrete strength, and the one which is based on the steel strength, which means the Nelson stud strength itself, a little bit lower. It's 9.57. So in this case, the one controls my design is going to be 9.57. And again, that was the difference between the two steel manuals. Older steel manual didn't show this value here for some reason. Looks like there's a typo or a mistake. Now in the recent manual, it shows this one, which really controls your design. Just to jump here for quick to this part of the table, now it says 1/2 inch, it's going to be 9.57 for F prime C of 4 KSI. Okay. So let's figure out now number of Nelson studs needed. For this beam here, if you take the 515, which is the compression in the concrete, and also the tension in the steel that you try to transfer from the steel to the concrete or the other way around. If you take this 515 kips, divide by 9.57, which means this is going to be a number of studs that you need to put on 1/2 of the span. Now we have roughly 54 studs in 1/2 of the beam. So I said here, in this side, I'm going to put here 54, and in this side, I'm going to put here 54 studs. Look at the span. The span is 30 feet. So the spacing is going to be very tight. I may end up by putting two studs next to each other. So I'm going to have rows. Each one will have two of them to keep the spacing in good shape. As it says here, you're going to end up with 53 equal spaces. Why? Because in each row, I'm going to have two studs. So I'm going to have total here of 54 times 2. In this case here, take the total span, divide by the spaces, you're going to end up with about 6.5 inches, as it says here, plus or minus. If you like to put one stud per row, you're going to have the spacing here is going to be very tight. It's going to be maybe 3¼ inch. This is not good. It's going to be too much for a welder to go there, age 3¼ inch and do one shot. But maybe 6.5 inch, I understand that this is just too many. And in reality, you may not need all of that. But this problem is based on the fact that you're shooting for fully composite action. And usually in all the problems here, we say, this is the way we start, we say, consider that you have full connection between the concrete and the steel to push you to use the full composite action. Okay, good. Now, I'd like to use the steel tables. In the steel manual, we have some steel tables for the composite beam. This is called here table 319 in the steel manual. If you have the book, you should be able to open it and look at it. Otherwise, I'm gonna put here sections of this table. Also, this table, I start to update it. So if I'm gonna move here a couple of slides, I'm gonna say this table here is the latest. The one that I have in the previous slide set with the older copy. So please feel free to erase the older copy and use this recent copy that I'm using. As you see here in the table, if I may just look here first, because I have a copy here of the table, it gives you here the beam size. So here's the beam size. It says W16 by 36. It also gives you here PMP, which means if this steel beam is used and you don't have any concrete topping, no composite action, this is going to be the capacity 240 kip foot. So actually you can take it from here if you want to. If you have W16 by 36 and the top is fully braced, you can take VMN from here. If you're doing ASD design, you're going to be using this green shaded column. It's going to be 160 kip foot. So this is nice. Now, how is this value calculated? If you like to double check it, you take 0.9, which is a phi factor, times F sub Y, 50 KSI. So this table here is for 50 KSI, times Z sub X. And with that, you're going to be getting here to this 240 kip foot. The good thing that this is going to be used here, if you like to check the steel beam capacity in construction condition. So the construction load case, you can just look here at this 240 and use it. You don't really need to do the entire analysis. You do phi times ZX, but it is also good from time to time that you remind yourself and do quick hand calculations just to confirm. It says here plastic neutral axis, which means about the plastic neutral axis location. It says here TFL, top flange. So the location of it is going to be at the top flange. I have a point that's called here point 0, right? Y1 is going to be equal to 0, and actually we call this point to be the first point. So let's call this point for now point 1. It's going to be point 2, point 3, point 4, point 5. What is this point 5? It says bottom flange. Not very clear to me, but I will understand all of this once I go through the sketch or the detail that we have for the composite beam, and then we'll figure it out. And for each one of these values, I have one Y1 value in terms of inches. And then after that, I have summation of Qn, which means the compression force. This summation of Qn is the same as this compression force that you are working with. It's the same as this C, excuse me. And then after that, you have the capacity. So this number here is going to be the capacity in kip foot. So this is going to be Vmn for the composite beam. For different Y2 cases, so if you have Y2 of 2 inches, it's going to be the capacity. Y2 is going to be equal to 2.5 inches, capacity is 415. If y2 equals 3 inches, it's going to be 435. So right out of this table here, you should be able to read PMN for the composite beam and for the non-composite beam. Non-composite beam is going to be this number here. And for the composite beam, it's going to be one of these that you can read or look it up. So I'm going to go back here one slide, a couple of slides to look at the table because we'd like to understand how it works. So in this table, you have a few variables. The first one here is called y sub 1. You see this y sub 1? It starts here to be 0. So the 0 point is going to be here, which is 0.1, top flange. Point number 5 is going to be the bottom flange. This is now the location of the neutral axis. So if you'd like here to get the full composite, you put your neutral axis right here at this location. So neutral axis location is going to be right on the top for full composite action. So I can draw here my line. So in this case, y1 equals to how much? I'm going to say equals to 0. So what happened? They have taken this top flange. Now let's zoom in. Here's the top flange. It's going to be right here. Here's the top flange of the beam. So this section here is going to be this section. And they cut it into 4 equal spaces. So you're going to be cutting here. You're going to say, okay, here's the first slice, second, third, and fourth. So you cut into 1, 2, 3, 4 equal spaces. If the neutral axis happens here in the top flange, I'm going to call this to be 0.1. And in this case, y1 equals 0. Now take the top flange and divide it into 4 equal spaces. So let's say the top flange thickness is 1 inch. Okay, I'm just throwing here a number just only for sake of discussion. It means if the neutral axis is going to be right here at 0.1, this y1 equals 0. If it's going to be at 0.2, y1 equals quarter of an inch. It's going to be at 0.3, it's going to be half inch. And here at 4, it's going to be 3/4 of an inch. It's going to be at 5, it's going to be an inch. This is, let's say, for some given beam. I don't know which beam size. I'm just throwing the number here so that we understand what is the meaning of this y1. So now I understand. I'm going to divide here this top flange into 4 sections, which means 5 points. The top point, I'm going to call it TFL, which means top flange. The bottom one is going to be bottom flange, which is 0.5. And this is TF, the thickness of the flange itself. I have another variable, which is this y2. So what is y2? Y2 is going to be the distance from the top flange all the way to the center of the compression block. So this here, my compression block. This is going to be the total thickness of the concrete. So for example, if I have W3 plus 2.5 inch concrete, this Y concrete is how much? I'd like to hear from you guys. If I have W3 plus 2.5 inch concrete above it,
5.5.
this is going to be 5.5 inch. So in case F, so I'm going to write it here. F, so it's not the right location. You can see here F, W3 plus 2.5 inch concrete. What's going to happen? Y concrete equals 5.5 inch. Okay. How about this Y2? How can I figure out Y2? You're going to see this Y2, if you like, is going to be equal to what? 5.5 inch, right? Minus A over 2. Does it make sense? Yeah, it's going to be this 5.5 inch subtracting A over 2. So at the beginning, you don't have this A over 2. So you can come up with an assumption, or you can figure out A, and then find out A over 2, and then find out this Y2 if you want to. Is it fine? Okay, good. Also in the table, I have seen other points. It says here 0.6 and 7. So I'm trying to understand what is this 0.6, what's 0.7. It says here at 0.7, the tension in the steel here, which means the force that you want to transfer from the steel to concrete. That's why they call summation of Qn at 0.7 is going to be equal to quarter of Fy times As. So actually, they come up with these points for me to give me this partial composite. So if the neutral axis is going to be right here, it's going to be fully composite. Once you go to any point rather than or other than 0.1, you're going to have here partial composite action. So you can control the amount of composite that you'd like to use in your analysis if you don't really need the full composite. And here's the reason. I'm going to take you back here to the previous example. In the previous example, in order for us to have this fully composite action, we put lots of studs. Now we are going to go back here and say, I don't need all of this moment capacity. This is just too much because the moment I have, let's say, is about 200. And this moment that you give me, the capacity is about 400, which means demand is 200, capacity is going to be 400. I'm providing double the amount of moment that I really need. So I don't really need all of that. So the question is, can I reduce the number of studs? And instead of having 54, can I have only 30 throughout the entire length, or just 40? Is this possible? Would this make it work? Now you're going to say, what should I do? I'm going to say, you put enough studs to transfer enough force. And this force doesn't need to be equal to the full tension force in the steel beam. So I say, okay, so what value should I use, right? So I'm going to say, if you put the neutral axis right here at this location, it means you're not really using the entire steel beam cross-section area when you calculate the tension force. So if you like to go with this 0.7, it means that you're using 25% of the steel tension force. Why? Because the steel tension force equals to Fy times As. So, okay. How about 0.6? It says here 0.6 is somewhere here in the middle. It's going to be equal to the average of whatever that you have in 0.5 and 0.7. Just say it's going to be the average. Okay. Let me go further to explain it more. I said, okay, let me take this. For some reason, this mouse jumps. If you like to use 0.1 in your analysis, it means that you have fully composite action. And look, the amount of steel that you're utilizing here now is going to be equal to the total cross-section area multiplied by F sub 1. I said, okay. How about 0.2? Let me zoom in. What happened in 0.2? 0.2, I'm going to be taking off the top quarter of the flange and not consider it in my analysis. And in this case, the cross-section area of the steel beam that I'm using, in this case, is going to be equal to the total cross-section area of the steel beam, subtracting the width of the beam times 1/4 of the flange thickness. I guess if you do this by hand, it's going to be really tough. This is why this table is much easier than using hand calculation. How about in 0.3? In 0.3, the amount of steel cross-section area that you're utilizing is going to be equal to As of the entire steel section, subtracting 1/2 of the flange thickness. So this shaded area is going to be the area that I'm going to be using in my analysis. How about here? You subtract here, or you deduct 3/4 of the cross-section area of the flange out of the entire steel beam section. How about here, 0.5? In 0.5, as you see here, the entire flange area is not coming into my analysis. So in this case, if I'd like to go here, I'm going to say now, the tension force that you're going to be using, right, which is going to be equal to summation of Qn, the total force that you need to transfer from the steel beam to the concrete section, is going to be equal to As. And what is As? Is going to be the total cross-section area of the steel beam, subtracting the area of the flange. This is exactly what I have in this analysis case. Here is going to be subtracting 3/4 of the area of the flange. Here is going to be 1/2 of the area of the flange is going to be taken out. And here is going to be total As that you can use in your analysis. So this case here is going to be fully composite, and all of these cases is going to be partially composite. Same concept, of course, applies to point number 6 and point number 7 that I didn't show here. So also point 6 and 7 is going to be what? is going to be partially composite with certain amount of composite action that you'd like to use in your analysis. I'd like to hear from you guys before I would go through the example.
Professor?
Yes.
So when you say, just to get things clear, when you say partially composite and that flange, whatever you take out of it, so that flange is not taking the shear force, or will be helping take more of the shear force that's being transferred?
This flange, you know the way it works? If you remember the way that we do the stress distribution on the steel beam itself, we say this steel beam is going to be under stress of F sub y. You remember that?
Right.
Okay. So let me open the older slide set. Here's the previous slide set. This is going to be number 5. In the stress distribution, okay, here's the equation that I was talking about. This one. Here's the stress distribution, right? That you're talking about.
Yes.
Choose this one. Just ignore this dashed line, like this center line and the plastic neutral axis location.
Okay.
We assume here that the entire steel beam is going to be under F sub y, and the whole beam here is going to be in tension. Okay? Now, in order for us to make this work, we need to have here 2 forces. So one force is going to be called compression force. The other force is going to be equal to the tension force. And we say they're going to be equal to each other, right? Let's say here in one numerical example, I'm going to throw here some numbers just to make it easy. The tension force was equal to 500 kips. Okay? Compression force is equal to 800 kips. To obtain full composite action, how much force I need to transfer from the beam to the concrete? Can you help me with this?
500.
500. Why not 800?
Because you only need 5. Wait, is that that's the?
This is the capacity of the entire cross-section area of the concrete. This is the capacity of the entire steel.
Well, because the concrete can take more, so you just need 500 maximum.
Okay, so in this case, you say, here's the compression area. I don't really need to have 800 kips. So instead, I'm gonna make my concrete section to take this compression is gonna be only taking 500. Why 500? Because the steel cannot take more than 500. So why should I use more than 500 when it comes to compression of the concrete? Doesn't make any sense.
Right.
So okay, good. Now, the moment capacity is going to be equal to this 500 times the distance from here to the center of this block. I'm going to be changing this to how much now? It's going to be 500 kips. Now, this is going to be here fully composite. If you are able to put some studs, some Nelson studs, you're going to put them there, right? What's going to happen? Now, this Nelson stud, you're going to design him for only 500 kips. And with that, you have fully composite section. Agree?
Agreed.
Okay, good. Now, after I did my analysis, I found out that phi mn, I'm gonna put here, phi mn is equal to, let's say, 600 kip-foot. Looking at my analysis, I see here some m sub u is equal to 400 kip-foot. Now, how do you feel about this? This is gonna be for the full composite. This phi mn for full composite, right? But I need only to cover 400 kips, which means this full composite is just too much for me. And the amount of studs I put there is going to be just taking the people's time, trying to weld them, you know, to each beam, you put all of the studs. So I said, okay, is it possible to reduce this Feynman to only 500?
Right.
You should be happy with 500 because you're still above by a lot than this M sub U, the 400 kip would. So I'm gonna say, how can I do this? I'm gonna say, you don't have to add lots of studs. So the steel beam size is the same, concrete is gonna be the same. But I'm gonna limit the amount of force to be transferred from the steel to concrete. And instead of 500 kips, I'm gonna make it, let's say, 450. Does it make sense?
Yeah.
So you know what? Let me cross this out. I don't need it. That was good for full composite. I'm gonna make here the tension force. Now this is gonna be full composite. Now here's the partial composite. I'm gonna put here the tension force. I'm gonna put it equals 450 kips. Now, how about the compression of the concrete? What value would you like to use? It has to be also 450 kips. You cannot go beyond this because this is now the maximum force that you like to transfer between here to there. Now what's gonna happen to your Feynman? Your Feynman is gonna drop down to what? Maybe 500 kip foot or something. So I'm gonna say in this case, in the partial composite, Feynman, excuse me, is gonna be equal to 500, let's say 500 kip foot. I'm just throwing numbers here for some given case, right?
Yes.
So I'm gonna say this is gonna be here partial composite, and with that I'm gonna be using less studs. Are you happy with this analysis?
Yeah.
You say, okay, great. So how would you make this to have only 450 kips? I'm gonna say the only way that you do it, because now you have F sub y throughout the whole thing, if you just take this cross-section area of the steel beam, look at this. I'm gonna be taking only this cross-section area of the steel beam, this section of it, and use it in my analysis. And this area here, I'm gonna be ignoring it. Good?
I see.
All right. How can I do this? I'm gonna say, well, I can have lots of degrees when it comes to this partial composite. And this degrees is gonna come by if, for example, in one case, I'm gonna say this is gonna be the area that you need to use of your steel beam. Or it's gonna be this area here. I'm gonna be taking it to here. Or it's gonna be this area here. Or it's gonna be this area here. It's gonna be based on some degrees, right, of this composite action. So the way that I would do it here is by limiting the amount of steel that I'm gonna be doing yielding analysis with it. How is that? If you go here to 0.5, you just take the flanges out, the top flange, and you don't use it as part of your AS. If you use the entire steel beam, it means that you're gonna be fully composite. Item number 2, you take off little section from the top. Item number 3, you take 1/2 of the flange thickness times the width of it, which means 1/2 of the flange force out of the picture. Here you take 3/4. Here you take the entire flange out. And then you multiply this tension is going to be equal to this AS, just to be correct, detail times Fy, if this makes sense to you. So the effective area here is going to be equal to the entire cross-section area of the steel beam subtracting the flange area times F sub y. This is the reason that they give me here plastic neutral axis location. Say if you're giving the top flange, it's going to be fully composite, which means that you use the entire steel beam. If you're going to go here to point number 7, it means that you're taking here only 25% of the steel beam cross-section area, right? If you like to use, let's say, point number 3, it means that you're going to be deducting 1/2 of the flange cross-section area and then do your analysis. Okay? Now let's see the example. Same beam that we are working with is W16 by 36. I'd like to use a table to figure out the capacity of this section. So I'm going to say W16 by 36. I don't have a value now for the A compression block depth. So I'm going to assume that is equal to 2 inches. Concrete thickness is equal to 4 inches. If you guys recall this, concrete thickness equals to 4 inches. So HS is the total concrete thickness, right? I'm going to go back here couple of slides. So Y concrete here equals to 4 inches. I assume that A equals to 2 inches. So in this case, this Y sub 2 is going to be equal to HS minus A over 2 is going to be equal to 3 inches. So now I know which Y2 I'm going to be using. Let me go back just to confirm what is Y2. Y2, the distance from the center of the compression block to the top of the steel beam. So, okay, good. Let me look here at this table. In this table, it says summation of Qn for this steel beam is going to be equal to 530 kips. Does it give you this? So this force here, if you, Y1 is going to be equal to 0. So this value here, when you are at the top flange, and this represents the full composite action. And say this row here is going to be for the full composite action, start from here. It's going to be here, full composite action. With this full composite action, if your Y2 equal to 3 inches, how much is Phi-man? 435. I'm guessing the answer here is 435. Total force that you need to transfer from the steel beam to the concrete is going to be equal to 530 kips. See, great. Now I have these two numbers. I have the total force 530 kips. What does it mean? How much now is A if I'd like to do the actual analysis? Now you have the slab thickness and you have the slab width. You have concrete strength. You have all the properties of the slab. So you need to say tension is going to be equal to compression. The compression force is 530 kips because equal to the tension force out of this equation here. Divide this by 0.85, divide by the strength, divide by 60 inches, which is the width of the concrete. Now end up with A now equals 2.6. I assume that A is going to be equal to 2 inches. It turned to be 2.6 inches. I can revise my Y2 analysis. Y2 is going to be equal to the same 4 inches. Subtracting 1.3 is going to be 2.7. Now I'm looking at this. Do you see here 2.7? No. But I see here it's going to be between these two values, right? If Y2 is going to be equal to 2.5 inches, your Phi-man is going to be 415. If it's equal to 3 inches, your Phi-man is going to be 435. Do interpolation with 2.7 and then figure out how much is Phi-man. Now Phi-man for full composite of this section is going to be equal to 423 kip-foot. How do I know if it's going to be for full composite? Because I picked the top flange. I picked Y1 equal to 0. That was my choice. I have chosen that I'm going to have here a full composite by just using the first point, point number 1, which is the top flange. And based on this, I have AS times F sub Y is going to be equal to 530 kip. Once you figure out the distance Y2, you can come up with Phi-man right directly, right away. Questions?
Sir, do we always have to pick Y1 as 0?
No.
Or when we...
No. Later on, we're going to change our mind. You're going to see it. I still have enough slides. I'm going to show you that, let's say I don't need all of that. So let me pick one of these points. Because look at this. If you're going to be going here with less, look at this. When you go here with less composite action, look how much the force is dropping. 530, 455. Let's say I decide to go with point number 3. Amount of tension force or compressive force that you need to transfer through the studs is going to be 380 kips only. And how much is Phi-man? It's going to be 400. So in case that you don't like the 435 because just is too much for you, you don't need all of that. And you'd like to reduce it to 400 kips foot, right? In this case, you can reduce the tension force or compression force, the amount of force to be transferred from tension to compression is going to be only 380 kips, and this is 530 kips. And with that, you reduce the number of studs.
So is it going to be given to us in the question, or do we decide it on our own? How many,
You can decide.
to take?
You can decide based on M sub U, because you need to have this is going to be here Phi-man, right? All of this number is going to be Phi-man. This is going to be the available strength in flexure, which means Phi-man. So it's going to be all based on M sub U. If M sub U, let's say for this section is equal to, I'm going to throw a number there, 390 kfoot. Let me put it here. M sub U equal 390 kfoot. How much is the force that you'd like to transfer or design your Nelson stud for? I'll let you figure this out yourself. Okay, let me work on it with you. Your M sub U, the demand is equal to 390 kfoot. I'm looking maybe at 3 inches, right? I'm gonna say, if I'm gonna go here with point number 4, this is not good. It's lower than 390. So I'm gonna stay here, maybe 400 kips or kfoot, right?
Okay.
It means the amount of force I need to design for studs is gonna be 380 kips.
Okay.
All right, that would just keep it simple. Let me move forward and see what can be done. Now the shear studs. I'm gonna go back here. Now I'd like to do here full composite, right? In this example, I was doing full composite, which means I need to take this 530 kips, design the studs for. All right, now I have 530 kips. I'm gonna go with 3/4 of an inch stud. The capacity here is 21.5. Total number of studs throughout the entire beam is going to be equal to 2 times the 530 kips divided by the stud capacity, 21.5. Now I have total of 50 studs to be used throughout the entire beam. The this tension or compression force that you divide by Q sub n for one stud is going to be for 1/2 of the beam span. This is the reason that we have this factor of 2, because you're doing it for the entire span. Okay. Okay, let me go here, next slide. One complete example. I have, it says here, select W16 by beam. F sub y is right here to resist the load. Concrete strength for KSI, slab thickness, 4 inch. No temporary shoring, which means your beam should be able to resist the construction life load without any supports. They give you here also construction life load. You have the dead load life load, you have the span, and they say the beam spacing, which means that you're going to have a beam here at 8 feet. And here's the stud size. Now you need to design this beam. So I'm going to say, first, let's figure out the demand. You see, you guys, you're good now with determining the demand, right? You know what's going on here. Here is the ultimate load. Here is ultimate moment, right? Here's the effective width of the beam. I'm going to say it's going to be 2 times the span divided by 8. Are we all good about this span divided by 8 times 2? Code says it's going to be 1/8 of the span on each side. I have 2 sides because this is intermediate beam. So I'm going to say times 2. It's going to be 7 feet. Center to center, it says here 8 feet. Where do I have this from? I'm going to say from here, 8 feet, center to center. Now, which one controls, the 7 feet or the 8 feet? I can say the smaller, of course. I'm going to be using here 7 feet, which means 84 inch. This can be the width of the flange, right? I don't know what beam size to work with. So I'm going to say, okay, let me assume first that I'm going to have here full composite action. Let me try here my analysis. I'm going to say AS times Fy is going to be smaller than this value, correct? This is going to be compression. This is going to be what? The tension. I'm going to be assuming first that this A is going to be equal to 1 inch, just for quick estimate at the beginning. Now, how much is phi min in a composite beam? Phi min in a composite beam, how do you do it? You say phi min is going to be equal to the tension force, which is going to be controlling your analysis, not the compression force. Give you this tension force, applied by D, depth of the beam, plus HS minus A over 2. Is this correct? Is this equation okay with you guys? or something is wrong with it. Anything wrong with this equation?
E by 2.
You by the 2.
Yeah, thank you. It's right here. So this is actually correct. See, it is done here correctly. Just this equation is incorrect. So what is the purpose of this equation here? Purpose is because I have the ultimate moment. This is how I started with. I have this ultimate moment. And I'm trying to figure out how much the area, the steel beam area needed. And based on this, I'm going to be going there through all the steel beam sections and pick the appropriate steel beam size. So once you put all the values here, you put m sub u divided by phi is going to get you here mn. Which means I'm setting up m sub u to be equals to phi man. And based on this equation here, I'm going to be determining here AS needed. So I'm going to say, okay, here's AS based on this equation. I have all of these values except for AS. As it says here, based on this analysis, AS is going to be equal to 7 square inches. It says here W16 by, I'm going to go back here one slide. W16 by in the top. I'm going to go here W16 by, steel properties, right? This is going to be the shape properties. I see here W16 by 26, it has cross-section area of 7.68. It works. So I'm going to start with this beam here. I don't really need to go 16 by 31. There is good difference between the two. And based on this quick estimate, I decide that I'm going to be going here with W16 by 26. So if you like to do hand analysis, this is going to be the way that you do it to come up with the first beam size. It's just quick estimate here for the beam size, right? After this, you continue your analysis if you want to. So, okay, now this is good. Now let me use here the table to figure out the capacity for quick. I have here 16 by 26. I'm gonna assume full composite, which means I'm gonna be here at Y1 equals 0. I know the slab thickness is equal to how much slab thickness? Anyone recalls the slab thickness? 4-inch, concrete strength, 4 KSI, and the width is gonna be 84 inches. Now, based on full composite, I have the force transfer from concrete to steel, which means the maximum tension in the steel, and the compression of the concrete is going to be less. It's going to be 384 kips. This is the 384 divided by 0.85. F prime C is going to be 4 KSI, and the effective width here is going to be the 7 feet, the 84 inches. I have my A depth, 1.34. Okay, now let me figure out Y2. You guys recall what Y2 is? Or should I go back and show it to you? Here's Y2. Y2 is going to be equal to total thickness of the concrete subtracting A over 2. So look at total depth of the concrete, the 4 inches, subtracting A over 2. It's going to be 3.5 inch. So great, I'm going to be going there. It means Vmn equals 327 for full composite. So if you plan to use W16 by 26 full composite, you should be good. Why? Capacity is 327 more than your M sub U, which is 303 kip foot. Where do I have this M sub U from? Okay, go here back 2 slides. Here's M sub U 303. So this is a quick method here, and with that you're able to find out the full strength based on composite.
So,
Action.
I have a quick question.
Yes.
For why was 3.3 rounded to 3.5 instead of being interpolated?
You can do interpolation, but it's gonna be very close because this 327, look at this, 312. So I looked at both of these two numbers, right? I say 3.5 is right here, 3 is gonna be there. How about 3.33? If you like to do interpolation, absolutely. It's gonna be maybe 320. But what I'm saying, based on this Y2, is almost 3.5.
Okay, so is it safe to do that
Alright.
when we're doing the homework? Or
No, in the homework, please be detailed. You do the interpolation.
oh, okay, thank you.
Right.
Professor, back on the previous slide.
Here?
Next one. The one that, yeah, the D, where did that 16 come from?
Oh, the depth of the beam is 16 inch, is right here, which is about here. Don't forget that this is kind of a quick estimate, right?
Okay,
This
so
is just to come up with the area needed.
So we
Because
just assume
yeah.
16.
Yeah, because I'm
Okay.
using W16. Because look at this W16. I didn't know at the beginning when I was doing this analysis here that I'm going to be picking W16 by 26 with a depth of 15.7.
Okay, makes sense.
So I was thinking it could be maybe W16 by 40 or W16 by 57 or W16 by 26. So I picked an average of 16 inch. Where's it coming from? From the beam side, it says W16 bar. This is just at the beginning as an estimate, not more.
Thank you.
No problem. So, okay. How about the non-composite during construction? I need to check that. Otherwise, my beam selection is not going to be good. I want to be sure that W16 by 26 has enough strength to support the construction load. Here is the life load. Here's the dead load. Ultimate is going to be this number here. Ultimate moment 77 kfoot. Now, do I have enough strength? Well, I'm going here through this analysis. But you know what? Let me take you here back one slide, and then I want you here to figure out the strength of this steel beam as a non-composite beam during construction. Can someone look up the value and tell me how much is the strength of it? The non-composite steel beam, how much is the strength of it, the PMN?
166
Yeah, where? Where'd you get it from?
on the table, like,
It's right here.
yeah.
Okay. So what I'm saying is you can just look it up here. Or if you like, you'd like to confirm the value, I'm doing it here. Here it is. 0.9 times 50 times 44.2. What is this 44.2? I'm going to say this ZX. From where? From the steel properties in the main section, in the first table. It turned to be exactly 166. Same as this one here. So it's going to be up to you now. When you're doing the homework, you can look it up from here and just say, based on table 3-19, W16 by 26, VMN for non-composite 166, you can just look it up. It's going to be fine, except. So you don't really need to do this analysis. You can just look it up in the table. So now I have no problem here with the construction life load when it comes to the beam size. Now I need to figure out number of studs.
Sir,
Yeah.
where did you get 8 feet from?
8 feet?
Yes, sir.
Good question. Let me see. You see here 8 feet, any place?
Beam spacing.
Okay, so the beam spacing was given as 8 feet, which means you're gonna have a beam here. Here is the slab, and you're gonna have beams running this way, right? The spacing from one beam to the other is gonna be how much now? 8 feet.
8 feet.
Yeah, it's gonna be like this. Okay?
Okay.
All right.
Okay.
All right, now I need to figure out number of studs. I know that the compression force based on full composite, 384 kips that I need transfer from tension to compression. I'm gonna go with 3/4 of an inch for KSI, 21.5 kips for the capacity of one stud. Total number is gonna be 2 times 384 divided by 21.5. Why 2? Because each side will need this compression force divided by the capacity of one Nilsson stud. I'm going to be using here 36 studs total for the entire beam span. We're good? All right. Now let me go back here one slide and look at the values. I'm going to go here 327 and M sub U 303. So it's right there. Did you do here the deflection analysis? How can I do here deflection analysis? Where is the moment of inertia for the steel beam? Should I use the moment of inertia for the bare steel beam, or should I consider composite action? Let's say, of course, if you consider composite action and you do this I transform, it's going to be much better because you're going to have higher moment of inertia. So you have the concrete, why don't you use it? With this amount of Nelson stud that you provide, you can say, yes, okay, this is great. You don't really need to do it by hand because we have tables for it. So this table here, based on Y2 and the depth and all the information that you just finished from the previous example, let's go here through this table. This is here in table 320. It says lower bound elastic moment of inertia. I lower bound for plastic composite sections. W16 by 26. I'm gonna go here with 0.0. You see this Y1 of 0, which means full composite. Y2 equal to 3.5 inch. Your moment of inertia is 796 inches of 4. I guess this is beautiful here. You don't have to find out the moment of inertia the way that we have done it last week. It's much simpler. You just find out here the moment of inertia for the transferred section, included the concrete effect, divided by n. The whole thing here is done for you. You just need to figure out how many studs you're going to put there. If you have full composite, you're going to be Y1 of 0. Here's the section 16 by 26. You have Y2 3.5 inch, 796 inches of 4 is going to be your moment of inertia. So great. Now let me do this analysis. Here's deflection due to dead load, deflection due to life load. Look at the moment of inertia. How much was the moment of inertia? 796. I'm looking here at this equation. Deflection due to dead load, it doesn't choose a 796. You see this? It shows 301. How's that? This is going to be the moment of inertia about the x direction for the steel beam only, not for the composite. But in here, it shows 796, which is I lower bound for composite. Do you guys know the reason of this? Can anyone help me with this? Why, when it comes to dead load deflection, I'm not using the composite action? And when it comes to the life load deflection, I'm using the composite action.
Because a huge part of the dead load is the concrete itself.
So what?
Because the concrete is plastic and cannot take load during construction.
It's because the live load is only considered once you have fully composite action.
Exactly. So when you apply the dead load, you remember when you apply the dead load, the beam has no composite action. So the beam starts to deflect and show you this dead load deflection based on the bare steel beam properties. There is no composite action at that time. It was during construction when the dead load deflection happened. Life load deflection is going to happen after the concrete is hardened and people is going to start to use the building. So deflection here due to dead load is going to be based on the bare steel beam only. No composite action here for the dead load. Let me here review the construction sequence with you. First, you have all the steel framing. You're going to put it all together. After that, you put the metal deck. No loads yet. It's going to be only the self-weight of the beam, which is very small. And also the metal deck. The metal deck is like 2-3 pounds. It's very light. During construction, you're going to pull the concrete. Now, no composite action yet. Now, the steel beam is going to start to deflect once you start to put the concrete in there. By the time when the concrete hardened, 100% of deflection due to dead load has occurred. Now the beam went down already. Not went down like on the floor, but went down mean deflected down a little bit. So the entire dead load deflection happened once you cast the concrete. but the concrete is not hardened yet. When the concrete is hardened, now the dead load itself, deflection has happened. You cannot take it back. It's kind of locked in. Now you start to apply the life load. But now the concrete has this composite properties. And the moment of inertia becomes larger. So again, when it comes to dead load deflection, what you need to do, your analysis based on bare steel beam, no composite action. So when you go here back to the steel properties, the section properties, moment of inertia equal to 301. When it comes to life load deflection, you need to use the composite properties. It's going to be this 796 inches of wood in your analysis. So I did my analysis. I compared deflection due to life load. I'm sure that you guys know how to work with this. Turned to be more than 300 L divided by 360. This is going to be 0.95. Not very good. So what should I do? I say, well, let me also look at the total deflection. So this is kind of, yes, I can maybe play a little bit with my numbers here and make it work. Maybe just fix my numbers a little bit, maybe it's very close. So engineering wise, this is the same. It should be fine. Look at the total deflection. Add the dead load deflection due to life load deflection. Now we are at 1.63. Your allowed here is for the total deflection is L divided by 240, which is only 1.4. This is not good. So you need to do something. One of the things that you can do is to provide 1/4 inch camber or maybe 1/2 inch camber. This 1/2 inch is going to be taken off the dead load deflection only. Why is that? You bring here the steel beam with camber, which means the opposite of the deflection. It's going to be going up like this. It goes up in the middle, let's say by 1/4 inch. Now you apply the dead load, which means the concrete weight is going to be there and the steel beam weight. Now the beam is going to deflect 0.68 inches. Now subtract 1/4 inch because the final deflection here is going to be 0.68 minus 0.25. This is going to be 0.43 inches. So roughly like 1/2 inch. Now deflection due to dead load is going to be only about 1/2 inch, 0.45 inches or so. So it's going to be only 1/2 inch. It's not going to be really 0.68. So that you may make it work. This can be okay. I mean, you may be able to make it work if you're going to be going even to 1/2 inch. Because look at the difference here between the 1.6 and 1.4. It's about 1/4 inch, the difference here. So if you provide camber of 1/4 inch or 1/2 inch, you should be fine. Your beam should be fine. I said, okay. Let me here assume that I cannot really provide camber. This is a different way of thinking, right? Because it's going to be up to you in your analysis and your project is going to be up to you. You can do camber, but your camber cannot be more than the deflection due to dead load, or maybe 90% deflection due to dead load. So I'm going to say here maximum camber. I'm going to put it here. .75 deflection due to dead load. Okay, give you the maximum camber so you guys have it in your notes. Unless you'd like to pump up the beam size. So I'm gonna go here to the next beam, W16 by 31. You say W16 by 31. How about the moment of inertia? You say moment of inertia 974. How do you read this? You say very similar table to this. It's gonna be W16 by 31. Look at 3.5 inch roughly, and for that, look at what happened from 796 to 974. Moment of inertia went up a lot. Can you figure out deflection again due to life load? Do you guys remember this equation? It's going to be moment of inertia of the first analysis, which means this one here. Let's say this is going to be this value here, right? And this value is going to be this moment of inertia for the new beam size. How about this 0.95? It's giving deflection, which is right here. Right? Take the old deflection, divided by the new moment of inertia, multiply by the old moment of inertia. With that, you get the new deflection. And this new deflection is good. It's going to make everything good. So shifting up or moving to a stronger beam, W16 by 31, could be also an option. So you
Sir,
may...
just a quick question. From where did we get this 360? N divided by 360 and N divided by 240. Are they checks or something?
This is code, and this one, we went through it already, I guess, in the steel beam design. This is code limits that we discussed for deflection limit. You see this? The allowable deflection
Yes,
due to
sir.
live load and due to total load. So this is actually
Okay, sir.
in slide set 4, slide number 11.
Okay.
Okay?
Yes,
All right.
thank you.
No problem. Now for this beam here, W16 by 31, I have the ultimate demand is 303, because now the question is how many studs I need to provide, right? 303 for full composite. Let me go here to next slide. Here is W16 by 31. Full composite, how much is the strength? You remember how many inches we were talking about in Y2? How many inches? 3.5. 392. Do I need the 392? That was a question to get full composite. Let me go back here one step. Full composite 392. Summation of Qn 457. Where is this at? Oh, the 457, which means this number here, right? How many studs? I need 35 studs. How about moment of inertia? What moment of inertia? The lower bound moment of inertia. Here is the lower bound moment of inertia in this case. It's going to be how much? 974. Do I need all of that? So you see, I'm checking here number of studs. In the same time, I'm checking Phi-man. Also, I do check here on the deflection on this 974. So it's okay if you want to go with full composite, everything is going to be okay. Everything meaning what? Phi-man satisfied, deflection satisfied. Why? Because you need to have a minimum of 812 inches of fall. How this is calculated out, I want you to go back here and figure this out. See this? This number here, this gives you the needed value, needed moment of inertia. So for full composite, everything is good, but you don't like that. Like what we discussed at the beginning, we said, I don't like that. I'd like to reduce number of studs. So I'm gonna go here to 0.6 for partially composite. What's gonna happen if I'm gonna go here to 0.6? Here is 0.6. How much is Phi-man? 307. Is this okay? You go back. Your demand 303. Now my capacity would become 307. It's kind of, yes, it's okay. But how about for the moment of inertia? I'm gonna go here, a couple of slides in front, and look here at moment of inertia for 0.6, 3.5, 691. What was my minimum? 812. So I said no. How about 756? Is this a good number? No, I'm looking for at least 812. I said, well, it's gonna be 0.4. How about if I'm at 0.4? Let me look here at the flexure strength for 0.4. Am I okay with 0.4, 342? I'm gonna say yes, because my minimum is 303 kip-foot. If you look here, 303 kip-foot. So it seems that 0.4 is gonna be the one. Now, let me move also one slide ahead. How much now is summation of Qn? Now you need to transfer 274 kips. Great, 274 kips. How many studs in this case? So K is gonna be how much? 21 studs. So I'm gonna go here with 0.4. I don't really need to have full composite action. So W16 by 31 is good. And instead of having 35 studs, I'm gonna be adding here 21 studs, and my beam is gonna be okay. And with that, I check deflection, I check capacity, I check number of studs. All right, I guess we're done. If you have any questions, go ahead please and ask and stay around. Otherwise, please sign up.
Professor, if the camber is already given on your beam, so we don't have to worry about dead load deflection then?
Yes, but don't forget that you have maximum camber. This maximum camber is going to be 0.75 of the dead load deflection. Yes, so you can do with camber if you want to.
Sir, I have some questions about the submitted, the
Yes.
course project. So
Yes.
can I ask them now or should I wait?
No, this is fine. Just give me 5 minutes, and then yeah, just stay around. If you guys have any questions,
Okay.
stay around, and otherwise you can leave. Stay around. Hang on.
I have a question for you really quick if you're still here.
Please, if you just give me 5 minutes, I'll come back to you. Thank you.
Okay.
Yes, I'm back. Yeah.
I just have a question about attendance. I was away from my computer